Well, it's Thursday. I'm making this video for tomorrow. We still don't know what the election is, but these things happen. So we should know in a few days. But in the meantime, we got more exciting stuff to talk about than the election. And today I'd like to talk a little bit more about this theory of line integrals we're doing. And begin with a little review. So there is a page that I posted that goes along with this, and I will try to kind of follow that page carefully and show you what's going on. So first of all, we are given a curve C, and we are given a vector field F, PQ. Each one of these is a function of X and Y. Everything we're talking about is in the plane. Here, I'll put that off to the side. So we'll talk about free space next week about this. And and then F perp is equal to minus QP. So Q minus P. There's an alternative here. You can use either one, but this is the left-hand rule that we talked about. There are advantages to using the left-hand rule and the right-hand rule. Okay, so a couple things here. We can take the derivative, for example, of these are two different vector fields. They're related, but they're different. But if we take the derivative of F, as it's a function of X and Y, we get a 2 by 2 matrix. And that 2 by 2 matrix is, we have two variables, X and Y. We have two coordinates, P and Q. Here, two coordinate functions. So this is the derivative of P with respect to X, the derivative of P with respect to Y, the derivative of Q with respect to X, and the derivative of Q with respect to Y. Now from linear algebra, I mean, we learned about the determinant in linear algebra, but you can also take the trace of a matrix. So if you have A, B, C, D, the trace is A plus D, the sum of the diagonal elements. And the trace star of A, B, C, D is equal to C plus B. So this is the off-diagonal trace, this is the trace. And these play important roles in lots of different mathematical things, but they will play a role today too. It's kind of interesting how some of these objects, like determinant and so on, play a role. Oh, this was a mistake. Now I can't use this for a while. But they'll play a role for us today as well. So while my board dries, let's take a look. So here we have the situation, and we would like to find the, we'll deal with this as a force field. And we'll want the force along C. So in order to find the force along C, this is the integral. Force is a vector. We'll dot product with a unit tangent vector along C. So T will represent a unit tangent as it has before. And this, if we have a parameterization, this will end up to be the integral of F of alpha of T dot alpha prime of T dt, and from whatever the domain is. And this is the force that is with you here. And another way to write this is the integral of P dx plus Q dy over C. So on my paper, I have the qualities running this way. This is a notation for this line integral, the force that's with you. With a parameterization, this is what it's equal to. And this is the basics of what we are computing here. If we look at the force across C, it changes somewhat. Since we are going across C, we are integrating with respect to N. And this ends up to be the integral of f perp dot t. So these are the same along C, which is equal to the integral of, using here the same idea. So this is q dx minus p dy along C. And if you parameterize, this is equal to the integral from a to b of f perp dot t. So this will be f perp of alpha of t dot product with alpha prime of t dt. So this is the basics of finding the force across C, finding the force with C, which is the work in this case. This is also work. It's force integrated with respect to distance. Measures a different thing. So this is where we start from. So the next thing in our agenda here is to find out how to actually do these things. The first thing we find is that if a force field is conservative, in mathematical terms, this means is a derivative. By is a derivative, I mean it's a derivative of some other function. So if the force field is conservative, then this integral of f dot t over C is equal to f of b minus f of a, where this f is the antiderivative. So f prime of x and y equals f of x and y. F is a real valued function, so its derivative is an ordered pair, pq, and if its derivative is f, then this is a derivative, namely the derivative of capital F. And this integral, the force that's with you, is just like in calculus, it's the antiderivative evaluated at b. This is the terminating point of C, minus f of a, where a is the initial point of C. So b is alpha of little b and a is alpha of little a, where the domain of alpha is ab, if you had a parameterization. But here you don't need a parameterization. So it's always a good idea to check if a vector field is conservative or not. If the vector field is a derivative, this is pretty easy. And this works for both of them. So if you're integrating f perp, so you're looking at the integral across now, even though this is tangential because you're integrating f perp, this is the same as f dot n. So f dot n is the same thing as f perp dot t. And this is again going to be f of b minus f of a if f prime of xy is f perp, is little f perp. So if a function has an antiderivative, maybe I should have called this capital F perp. It's not the same because this one has its derivative being f perp. So if the basic thing is that if a function has an antiderivative, this is how you find the line integral. So this is called the fundamental theorem of line integrals. And last time's homework, I think 28 is about that. Always a good idea to check if your vector field is conservative. So now what we'd want to look at is the following. We want to look at what happens if our curve is closed. And I'm going to begin with a curve that is called simply closed, meaning that it doesn't have loops in it. So it's one-to-one except at the endpoints. So A equals B. The beginning here equals the end. So a simple closed curve will enclose a region D, and there's a relationship between the integral of a vector field around or across the boundary and what's happening inside. In a sense, what's happening in both cases, maybe easier to look at if you're looking at a cross C, is that what is happening on the boundary is determined by what happens inside. So if things from the inside are moving out, that shows up on the boundary. And this is the essence of what's known as, or of what's called Green's theorem. We'll talk about two versions of Green's theorem. I'm going to erase the picture here, but this is the setup. And we're going to either integrate along this curve C or across this curve C, and we'll orient C to be counterclockwise. If you orient it the other way, you get the answer will be the negative of what you get. So that usually you establish that a positive route around C is counterclockwise. So here we go. So the first version of Green's theorem, and I refer you to your sheet again. This is at the bottom here. So if you integrate around a closed curve C, so A equals B on the C's that we're dealing with here. If you integrate a closed curve C, so F dot T, this integral will be equal to the integral of P dx plus Q dy along C. Green's theorem says that this is equal to the entire integral over the entire region G of Q sub x minus P sub y. So this is an area integral. You might say D area here. This A is different from this A. But this is a two-dimensional integral. This is a double integral we're talking about here. The book would have a second one here. And this is a line integral, so this is just over a curve. So these are quite different objects. This is integrating over the entire region, and you integrate this real valued function over the entire region. And this will give you the line integral. So this is looked at usually as a way to integrate line integrals without parameterization. If you don't have a parameterization, you can integrate over D. Now, integrating over D often involves another parameterization of sorts. So both of these can be work. But the fact that they're equal allows you to transfer one to the other, and you have a choice here. And this is often a good way to compute line integrals. Or if a line integral is complicated, sometimes it's a good way to do the other way around too. So this is the first version of Green's theorem. The second version, if you're looking at the integral of across this C, So this is the integral of f perp dot t. And if you compute this, this is the integral of q dx. I want to make sure to get this right, minus p dy. Yeah, q dx minus p dy. And this is over c, so this is this line integral. And this is equal to the negative of the integral over the region D. So again, a double integral of the partial derivative of p with respect to x plus the partial derivative of q with respect to y. So there's a nice relationship. There's an easy way to convert any of these line integrals around closed curves to an integral over the domain that that curve is encompassing. And there's one more thing I wanted to show you about this. So I'll give you some exercises from the book which do this. They don't talk about the integral across the boundary, but I will give you some exercises there too. But there's one other interesting thing here, and that involves this ladder integral. So the integral across being this, let's just write just that down. So here's the integral across. And this is something. Let's see what this is. So if we take f of x and y, that's equal to p of x and y, q of x and y. It's a vector field. And if we look at its derivative, f prime of x and y, this is the derivative of this p with respect to x, the derivative of this p with respect to y, and the derivative of this q with respect to x, the derivative of this q with respect to y. So there's the full derivative. And what we are integrating here in Green's theorem is the trace of the derivative. So this last integral is minus the integral of the trace of f prime over d. So the trace of f prime gives you this. And notice that this integral was also equal to the integral of f perp dot dt. That's over c. So if you're integrating f perp dt, this is the same thing as integrating the trace of f prime, f and f perp. So there's a relationship between f and f perp here that continues. If we look at the other one, it's similar. So if you look at the integral of f dot t over c, this is the number one we just dealt with a second ago. This ends up to be the integral over d of q sub x minus q sub x minus p sub y. And this is Green's theorem at work here. And let's see what this guy is. Q sub x, p sub y. And if we look at f of x and y prime again, p sub x P sub y, q sub x, q sub y. This doesn't really fit here. Q sub x is here, P sub y is here, but you have this negative sign. Let's look at F perp. F perp of x and y is Q minus P. And so F perp, let's take its derivative. This will be a Q 2 by 2, Q sub x, Q sub y, minus P sub x, and minus P sub y. And we are integrating here Q sub x minus P sub y. So we're looking at the trace of F perp. So this integral right here ends up to be the integral over d this of, and this is a minus the way we did it. So this end up to be the integral over d of the trace of F perp prime. So there's a nice relationship between these two guys. There's no minus. The minus is on this one. So the integral of around is equal to the integral of the trace of F perp prime. The integral of across is equal to the integral of the trace of F prime with the negative in there. So these are some nice relationships between line integrals, double integrals, and a little bit of the linear algebra of derivatives. We'll do some problems with this. Have a look at the sheet. See you tomorrow. Makeup should be up by now, by the way.